You are sitting here right now, watching this video, likely taking it for granted that you exist and that this video exists as well. Maybe you're viewing it on your phone, alone in your room, and everything feels ordinary, familiar, unquestionable. The walls around you seem solid. The floor beneath you feels firm. Your body feels real. All of it appears stable, reliable, undeniably there. But here's where things begin to unravel. Physicists are no longer fully convinced of that certainty. In fact, some of the most brilliant minds alive, people who have spent decades trying to decode the deepest structure of reality, are now saying something profoundly unsettling. They're not just claiming the universe is weird, confusing, or counterintuitive. We've heard that before. What they're suggesting now is far more radical. They're saying the universe might not exist at all, not in the way we assume it does, maybe not as something out there, not as a physical stage filled with objects moving through space and time, not as an objective reality that would continue exactly the same way if no one were around to experience it. And this isn't some flashy science fiction fantasy or a cheap clickbait idea. These questions are being taken seriously in academic research, debated at physics conferences, and published in peer-reviewed scientific journals. What started as small fractures in the foundations of physics, odd results from quantum experiments, contradictions involving time, space, and causality, slowly expanded into something far more extreme than anyone anticipated. A growing body of work now suggests that what we call reality may be nothing more than relationships, computations, or experiences with no underlying physical substance at all. In this video, we are going to examine real scientific research, experimental findings, and philosophical consequences that many physicists hesitate to discuss openly. We are not here to recycle tired quantum cliches or casually claim that everything is an illusion. Instead, we will look at how serious scientists build rigorous models proposing that the universe, as humans have always imagined it, may not truly exist. According to these ideas, everything we take for granted could function more like a user interface, similar to the icons on your phone screen, which don't reveal the true complexity of the electronic processes underneath, but instead hide them behind something simple and useful. And by the end of this exploration, you may find yourself asking a disturbing question. If the universe doesn't exist in the way we think it does, then what does exist? Because if space and time emerge rather than exist fundamentally, if particles are merely vibrations in invisible fields, if reality itself depends on observation, then the unavoidable question becomes who or what is doing the observing? To understand how we reach this point, we need to go back to the beginning. We need to trace the path taken by physicists who were bold enough to challenge assumptions that almost no one questions. What if there never was a universe in the first place? Let's begin with something most people never doubt: the belief that there is a world out there, a physical, solid environment that exists independently of whether anyone is looking at it. This assumption underlies nearly everything we do. You place your hand on a table, and it feels hard. You drop your phone and it falls. You look up at the stars and assume they are genuinely there, burning in distant space. But buried inside this assumption is a simple yet uncomfortable question. Not what you believe, not what you were taught, not what works well enough for daily life. How do you actually know that what you see, touch, and hear exists independently of you? You might answer, because I can see it. But that answer already misses the point. What you experience is not reality itself, it's perception. And the deeper we investigate how perception works, the more disturbing the picture becomes. Your brain does not present the world to you directly. It constructs a model of the world, a prediction, a simulation. It takes electrical signals from your eyes, ears, and skin and assembles them into something coherent. And that word, assembles, is crucial. You are not seeing reality as it is. You are seeing a simplified, abstract version that has been filtered, interpreted, and edited for survival. This isn't philosophy, it's neuroscience. Color, for instance, does not exist in the external world. It exists in your mind. Light itself has no color, only wavelengths. There is nothing inherently red or blue about those wavelengths. They're just energy. Color is your brain's internal translation of certain frequencies into a visual code that happens to work for humans. Other species decode light differently, or not at all, depending on their biology. Sound works the same way. Air molecules vibrate, but the sound of a voice or a car horn only comes into existence when your brain converts those vibrations into something meaningful. The world you believe you inhabit doesn't truly exist out there. It happens inside your head. Now take this one step further. A growing group of scientists and philosophers, including cognitive scientist Donald Hoffman, argue that the brain doesn't merely simplify reality, it may completely conceal it. Hoffman's research suggests that evolution does not reward accuracy, it rewards usefulness. In other words, your perceptions didn't evolve to show you the truth, they evolved to help you survive. Think of it like a computer interface. When you drag a file into a trash icon on your desktop, you aren't literally moving digital components into a bin. The icon is a metaphor, a convenient visual shortcut hiding an enormously complex process. According to Hoffman, reality functions the same way. Every object, every color, every shape you see is an icon, a user interface that allows you to interact with something unimaginably complex beneath the surface. We don't see the truth. We see what we need to see to stay alive. Just as file icons help you navigate a computer without understanding the underlying circuitry, perception helps you survive without revealing the true nature of existence. As strange as this sounds, it aligns disturbingly well with quantum mechanics. Hoffman's team ran mathematical simulations showing that agents who perceived reality accurately were consistently eliminated by evolution. They lost every time. The survivors were those who perceived nothing close to the truth, only simplified, useful representations. So what if this table isn't solid? What if your phone isn't really here? What if the stars, the sky, your hands, and your voice are nothing more than visual effects generated by an internal system that bears no resemblance to what you think it is? This idea may not be metaphorical. It may be physical. For centuries, people believed that the universe was built from particles, tiny, indivisible pieces of matter moving through space, colliding and interacting. Electrons, quarks, neutrinos. This framework still dominates everyday language about physics. But here's the reality. Particles don't actually exist in the way we imagine. In modern physics, there are no tiny dots flying through space that directly correspond to experimental observations. What we call particles are merely visible outcomes of something deeper. They are not the foundation. They are effects, temporary manifestations produced by excitations in underlying quantum fields. This is no longer speculation. It is the accepted framework of particle physics. The Standard Model, which successfully explains all known particles and forces except gravity, is entirely field-based, not matter-based. Fields are continuous entities that permeate all of space. Every particle you've ever heard of, electrons, photons, Higgs bosons, is simply a ripple in its corresponding field. Picture each field as an invisible ocean filling the entire universe. When the ocean is calm, nothing appears to exist. But when it vibrates in a particular way, ripples emerge. Those ripples are what we detect as particles. An electron isn't a tiny sphere moving through space. It's a localized disturbance in the electron field. A photon is a disturbance in the electromagnetic field. At its most fundamental level, the universe is empty, not made of objects, but of potential. Everything you see is built from interactions between fields. And these fields behave in ways that defy classical intuition. Quantum fields are inherently uncertain. Their behavior is probabilistic, not fixed. Even in their lowest energy state, the vacuum, they fluctuate constantly. These fluctuations aren't hypothetical. They can be measured. They produce real effects, such as the Casimir effect, where two metal plates placed close together in a vacuum experience a tiny force caused by energy in the empty space between them. So pause for a moment and absorb the implication. Even what we call nothingness is not truly empty. What appears to be absolute absence is, in reality, teeming with activity, vibrating beneath the surface of existence itself. Particles constantly emerge and vanish. Fields flicker, fluctuate, and interact below any direct level of detection. Even the most barren regions of space still contain the raw potential for everything that exists. This means that emptiness, as we normally understand it, is a fiction. What we assume to be the final, unchanging backdrop of reality turns out to be a restless, energetic arena. Nothing is static. Nothing is inert. The last supposed constant of our world reveals itself as yet another illusion, another active process disguising its true nature. The foundation we once believed to be passive and void is instead overflowing with energy and possibility. This realization strikes at the very idea of non-existence itself. You might now wonder, if the universe is built from fields rather than solid matter, why does the world feel solid at all? The answer lies in scale. Solidity is a macroscopic effect. It emerges because atoms, composed mostly of empty space, interact through electromagnetic forces. When you press your hand against a wall, no solid objects are colliding. What you experience is the repulsion between overlapping energy fields. Two organized distributions of energy resist being pushed into the same configuration. Hardness is not a property of matter. It is a sensation produced by quantum rules playing out within complex, structured systems. And this realization overturns everything we thought we knew. If there are no solid objects and no genuine physical contact, then our most basic experience of interacting with the world is fundamentally flawed. Think about it. Every memory you have of touch, from a handshake to the sensation of standing on the ground, is built on a misunderstanding. You have never actually touched anything. At no point in your life have you experienced direct contact. You have always been separated from the world by invisible force fields. Every interaction you have ever had was an interaction at a distance. What feels like closeness is an illusion produced by electromagnetic repulsion. The tactile world you believe you inhabit is a phantom construction. And this erosion of boundaries goes even deeper. What we label as objects, chairs, atoms, even people, are not truly discrete entities. They are temporary configurations of energy, stabilized by underlying laws we cannot see. There is no sharp line dividing you from the rest of reality. You are not a sealed container moving through space. You are part of an ongoing process. At every moment, you exchange energy, particles, and information with your surroundings. The air you inhale contains atoms that once belonged to other living beings. The carbon in your body was forged inside stars billions of years ago. At the quantum level, the distinction between you and not you becomes increasingly vague. Where exactly does your body end and the surrounding air begin? Which atom marks that boundary? The honest answer is that there is no such line. The boundary you feel between yourself and the universe is not a physical boundary. It is a conceptual one. It is a mental shortcut created by your brain so that you can function as a coherent agent. But fundamentally, you are not separate from the world. You are the world, experiencing itself from a localized perspective. You are not a drop within the ocean. You are the ocean, briefly shaped as a drop. This perspective dissolves the idea of an isolated observer. It transforms us from independent entities into interwoven patterns within a single, continuous fabric. Even the concept of individual particles begins to collapse under scrutiny. In field theory, saying that an electron here is the same as an electron over there is not a metaphor, it is literal. There is no this electron and that electron. Electrons are indistinguishable because they are not separate objects. They are excitations of the same underlying field. What appears to be a multitude of particles is simply the same basic vibration manifesting repeatedly. In a very real sense, all electrons are one and the same. Not copies, not replicas. The same pattern arising in different locations because the field itself exists everywhere. This implies that the distinctions we draw between objects may be inventions of the human mind. What we experience as separation, this particle versus that object versus the next, is simply how our brains carve a continuous, fluid system into manageable pieces. Now consider the implications. If the fundamental components of your body are not unique, but merely recurring expressions of universal patterns, then what makes you unique at all? The answer seems to be structure, your specific arrangement. But even that structure is composed entirely of interchangeable parts. This realization undermines not only the uniqueness of objects, but the foundation of individuality itself. We like to think of ourselves as singular, irreplaceable beings. Yet we are constructed from the same basic elements that form stars, rocks, and distant galaxies. When we assemble all of this together, a disturbing picture emerges. The world we perceive is not reality as it truly is. Perception is a user interface, fine-tuned by evolution for survival, not for truth. This interface presents us with a world of solid, separate things. But physics tells a very different story. At the deepest level, there are no objects. There are only quantum fields. What we call matter is nothing more than localized vibrations within those fields. What we experience as solidity is the mutual repulsion of energetic patterns. No genuine contact ever occurs. The boundaries we draw between objects, including ourselves, are artificial constructs. We are inseparably connected to the universe as a whole, and even the fundamental constituents of that universe lack individuality. All particles of a given type are simply interchangeable expressions of the same underlying field. Every pillar of our intuitive understanding has collapsed. Matter, solidity, contact, separation, individuality. Each one turns out to be another layer of illusion. A structured deception that allows us to function within a reality whose true nature remains concealed. We exist inside a coordinated hallucination. Nothing is truly solid. Nothing is fundamentally separate. Nothing is unique in the way we instinctively believe. Everything you consider to be the stable foundation of reality, the ground beneath you, the table supporting your computer, even your own body, is composed of emptiness, organized by invisible rules. A choreography of energy unfolding in the void. And this is not abstract philosophy. It is a direct consequence of the most successful scientific framework humanity has ever developed. We are forced to confront the fact that the most basic aspect of our experience, the materiality of the world, is an illusion. This is the first and most devastating layer of deception. Recognizing it triggers a profound existential unease. The ground seems to dissolve beneath our feet. The dependable, predictable world evaporates, leaving only structure and emptiness behind. Everything we trusted turns out to be a ghost. And if even matter itself is a deception, what remains reliable? This realization doesn't merely revise our understanding of the world, it shatters it, and it compels us to confront an even more disturbing question. If matter is illusory, what about the stage upon which this ghostly drama unfolds? We are accustomed to treating space and time as absolute, unchanging containers within which the universe exists. Space is the void that holds everything. Time is the river that carries all events forward. These concepts are so deeply ingrained that imagining a reality without them feels impossible. They are the operating system of our thinking. But we have just watched the illusion of matter collapse. The actors on the stage have vanished. Now we must find the courage to ask the next question. Does the stage itself exist? What if space is not emptiness, but something entirely different? What if time is not a flowing river, but another elaborate illusion? We are shifting from the question of what the world is made of to the question of where and when it exists. And the answer offered by modern physics may be more unsettling than anything we have encountered so far. Brace yourself. The next idea doesn't just challenge intuition, it dismantles reality itself. We are about to explore the possibility that space-time, the vast arena of the cosmos, is the greatest illusion of all. We now stand atop the shattered foundations of the material world, staring into the abyss. Yet even here, within this apparent emptiness, we feel as though one final support remains. One last unquestionable arena in which events unfold: space. We treat it as an absolute given, a smooth, continuous vessel that holds all existence. In our minds, we can divide any region of space in half, then divide it again, endlessly. Intuition tells us this process has no limit. Space appears to be infinitely divisible, an analog background underlying all reality. But what happens when we subject this assumption to our most powerful scientific theories? What occurs when we force Einstein's general relativity, which describes the geometry of space, to coexist with quantum mechanics, which governs behavior at the smallest scales? The conclusion is unavoidable. The structure collapses. The equations spiral into meaningless infinities. Our mathematical tools simply stop working. But this breakdown is not a failure. It is a signal. It points to the existence of a hard boundary, a fundamental limit beyond which our familiar notions no longer apply. there exists a scale at which the very idea of space loses its meaning. This boundary is known as the Planck length, approximately 1.6 x 10 to 35 meters. To grasp how unimaginably small this is, picture an atom expanded to the size of the entire observable universe. At that scale, the Planck length would be comparable to the size of a tree. Below this threshold, geometry itself stops functioning. Concepts like distance, position, and location dissolve into quantum uncertainty. Space is no longer smooth. It fractures into discrete, indivisible units, quanta of space, the pixels of reality. What we experience as a continuous universe is nothing more than an image with a finite resolution. We live inside something that behaves like a digital picture, appearing analog only because we cannot perceive its individual pixels. Space is not infinite. It has a minimum scale, a smallest possible unit. Reality, in this sense, is an image. And once we accept that, a crucial question immediately arises. If space is made of pixels, what lies between them? And what generates the image itself? The idea of pixelated space alone is enough to dismantle our worldview. But it merely prepares us for an even more unsettling revelation, one that shows these pixels are connected in ways that completely defy the rules of space as we understand them. This phenomenon is known as quantum entanglement. Imagine two particles created together so that their properties are intrinsically linked. For example, their spins must always be opposite. If one points upward, the other must point downward. Now separate these particles and send them to opposite ends of the galaxy, billions of light years apart. According to classical intuition, measuring one particle should have no immediate effect on the other. Any influence should be limited by the speed of light. But quantum mechanics predicts the opposite, and experiments confirm it with perfect accuracy. The moment you measure the spin of the first particle and find it pointing up, the second particle's spin instantly becomes down, no matter how far away it is. There is no delay, no signal traveling through space. The correlation appears immediately. This seemed impossible. Einstein despised the idea. He famously called it spooky action at a distance, and believed it demonstrated a flaw in quantum theory. He assumed particles carried hidden instructions determining their outcomes in advance. Decades of experiments have proven him wrong. There are no hidden variables, no pre-written scripts. The particles genuinely influence each other instantaneously, completely disregarding distance. This violates the principle of locality. It demonstrates that, at a fundamental level, connections exist that do not reside within space at all. They do not travel through space. They simply ignore it, as if space does not exist for them. This means the universe is fundamentally non-local. Beneath the surface lies a deeper layer of reality, where everything is interconnected in a way utterly alien to everyday intuition. For years, this baffled physicists. How could two particles remain connected across cosmic distances without exchanging any signal? How could causality survive such behavior? Recently, a radical and astonishing idea emerged that may offer an explanation. What if entangled particles are not communicating through space at all? What if they are directly connected through an underlying geometric structure, a hidden tunnel, a microscopic bridge? This proposal is known as the Riedrauch-EPR hypothesis, introduced by physicists Juan Maldacena and Leonard Susskind. EPR refers to the Einstein-Podolsky-Rosen paradox, which describes quantum entanglement. ER refers to Einstein-Rosen bridges, more commonly called wormholes, theoretical tunnels through spacetime. The hypothesis suggests that these two concepts are actually the same phenomenon viewed from different angles. Quantum entanglement and spacetime geometry are two expressions of a single underlying reality. When two particles are entangled, they may be connected by an extremely tiny wormhole. Their instantaneous correlation is not action at a distance, it is a direct connection. They are far apart in ordinary space, yet adjacent within this hidden network. Now extend this idea further. If every entangled pair of particles forms a microscopic Einstein-Rosen bridge, then the entire fabric of space itself may be woven from these quantum threads. Imagine a vast web composed of countless such connections. At large scales, this web appears smooth and continuous, but at its foundation, it is built from discrete quantum links. Space, then, is not emptiness. It is structure, a complex emergent network generated by entanglement. It is not fundamental. It arises from deeper, non-local interactions. The void we once imagined as empty turns out to be one of the most intricate structures conceivable. If space is woven from entanglement, our understanding of distance must be completely rethought. We are used to treating distance as absolute. A meter here is the same as a meter anywhere else. But in this new framework, distance is no longer primary. It becomes emergent. Distance becomes a measure of connection. Two regions of space are close if many quantum degrees of freedom are entangled between them. They are far apart if those connections are sparse. What we call physical distance is simply a macroscopic reflection of the density of these underlying quantum links. Consider a thought experiment. Take 2 points in space and gradually destroy the entanglement between them. To our senses, nothing unusual would occur, but at the fundamental level, those points would begin to separate. Space between them would stretch, not because they are moving, but because their informational connection is weakening. Conversely, if entanglement between distant regions could be increased, space itself would contract, creating a shortcut. This implies that space is not a passive background. It is dynamic. It can be assembled and dismantled through the manipulation of information and complexity. Think of social networks. Two people may live on opposite sides of the planet, yet feel close because they share many connections. Their distance is not measured in kilometers, but in relational density. Perhaps the universe works the same way. The distances we measure with rulers may only be crude approximations of a deeper informational geometry. Space is not where things exist. Space is how things are connected. This insight leads directly to one of the most profound and unsettling ideas in modern physics, the holographic principle. Originally proposed by Gerard 't Hooft and further developed by Leonard Susskind, it arose from studies of black holes. Physicists discovered something astonishing. The maximum amount of information that can exist inside a region of space is not proportional to its volume, but to its surface area. It is as if everything inside your house could be fully described by information written on its walls, with nothing inside at all. This led to a staggering conclusion. Perhaps our entire three-dimensional universe is a hologram. A hologram is a two-dimensional surface that generates a three-dimensional image. According to the holographic principle, reality may function in exactly this way. All information describing our seemingly three-dimensional world, galaxies, stars, planets, and ourselves, could be encoded on a distant two-dimensional boundary at the edge of the universe. Depth, motion, and volume would then be emergent illusions produced by this flat informational structure. We may not live inside a three-dimensional universe. We may be the projection it generates, shadows cast by a deeper reality. This is not poetic speculation. A powerful mathematical framework, known as the ADS-CFT correspondence, demonstrates that a theory of gravity in a higher dimensional space can be mathematically equivalent to a quantum field theory without gravity on a lower dimensional boundary. This proves that the holographic principle is not only conceivable, it is mathematically consistent. The psychological effect of this realization is profound. The world that felt solid, spacious, and undeniably real may be nothing more than an elaborate projection from an unseen screen. We may be characters in a three-dimensional film whose script exists in 2 dimensions. We have dismantled space by revealing it as an emergent holographic construct, but its partner remains. What about time? Time feels even more fundamental than space. It is the relentless flow, carrying us from past to present to future. It is woven into every experience. Yet, just like space, time disappears when physicists attempt to describe reality at its deepest level. One of the central equations in efforts to unify quantum mechanics and general relativity is the Wheeler-DeWitt equation. It describes the quantum state of the entire universe. Strikingly, time does not appear in it at all. According to this equation, the universe does not evolve in time. It simply exists, static and eternal. All possible configurations of the universe, from its beginning to its end, coexist simultaneously in a timeless landscape of possibilities. This realization induces a sense of suffocation. If time does not exist fundamentally, then everything that has happened, or will happen, already exists. The future is fixed. Free will dissolves. Yet we undeniably experience the passage of time. We remember the past, not the future. We feel motion, change, and progression. Where does this sensation come from? This vanishing of time is one of the deepest puzzles in physics. It suggests that time, like space, is not built into reality. It is created, perhaps by us. The most intimate feature of existence, the feeling of moving through moments, may be the grandest illusion of all. This leads to the concept known as the block universe, or eternalism. In this model, time is treated as another dimension, similar to space. Just as all locations in space exist simultaneously, all moments in time, past, present, and future, exist at once. The entire history of the universe forms a single four-dimensional structure. Your birth, your memories, this moment, and your death all exist equally within this unchanging block. Consciousness moves through it like a spotlight, illuminating one slice at a time, creating the illusion of flow. We do not move through time. We experience what already exists. Like reading a book, all pages are present at once, yet the story unfolds sequentially to the reader. Or like watching a film, where every frame already exists, but the projector displays them in order, creating motion. This view follows naturally from relativity, which shows that simultaneity is not absolute. Different observers disagree about what is happening now. The only consistent resolution is that all events exist. This produces a chilling sense of inevitability. If the future already exists, what meaning do choice and action have? We become actors following a script already written. Life becomes a path traced across a pre-existing map. And as unsettling as this may be, it is a logical outcome of our best theory of gravity. Still, a mystery remains. If all moments exist equally, why do we experience a clear arrow of time? Why do we remember yesterday but not tomorrow? Why do eggs break but never spontaneously reassemble? The answer comes not from fundamental physics, but from statistics, the second law of thermodynamics. In any closed system, total entropy, a measure of disorder, tends to increase. The universe began in an extraordinarily low entropy state. Since then, it has been moving toward increasing disorder. This progression is what we perceive as time. The arrow of time is not a fundamental law. It is a statistical trend. Order is rare. Disorder is overwhelmingly likely. Imagine all the air in a room compressed into one corner. That is a highly ordered state. Given time, the air spreads evenly. There are vastly more disordered arrangements than ordered ones, so the system inevitably moves toward chaos. This process is irreversible. Our universe behaves the same way. It moves from order to disorder. And this movement is what we call time. Our existence depends on this process. We are temporary islands of order, sustained by the consumption of order and the production of disorder. We are patterns that can exist only during entropy's rise. The flow of time we feel is simply the echo of this decay, the sound of a universe slowly unraveling. Now take a step back and look at what's left standing. We started this journey believing that space and time were a fixed stage, an unchanging arena where reality unfolds. That stage has fallen apart. Space isn't fundamental, it emerges. It rises out of quantum relationships the way an image appears on a screen. Its apparent smoothness hides an underlying granular, pixel-like structure. Its geometry may reflect information and entanglement rather than literal distance. It might even be a holographic projection. Time is no better. It is not a fundamental flow. At the deepest level, it may not exist at all. The universe could be a static, four-dimensional block where every event, past, present, and future, exists simultaneously. And the arrow of time, the irreversible feeling of forward motion, may not be built into the universe itself. It may be a statistical drift toward higher disorder in complex systems like us. Space and time aren't the container we live inside. They may be something we, or the system itself, generate. A product, a byproduct, a side effect of deeper, more abstract rules that have nothing to do with how reality feels to human intuition. They aren't the stage. They're part of the set design. And just like the illusion of matter, they function as a user interface, an operating system that lets us interact with whatever reality really is without ever understanding its true architecture. It gives us here and there, before and after. But behind that operating system is something entirely different, something neither spatial nor temporal. We are forced into a conclusion that is almost impossible to accept. There are no truly solid things, and there is no truly solid stage for them to exist on. Everything we've ever called the universe, its matter, its space, its time, may be a multi-layered interface, a sophisticated representation generated for us or by us from a deeper structure that is fundamentally beyond comprehension. And that realization triggers a deep existential dread, a sensation of total disorientation. If the world we experience is not reality itself, but only a representation, then where are we actually located? If there is no genuine here or now, then what are we? We start to feel like digital avatars inside a game, whose rules we don't understand and whose designer we've never met. Every action becomes questionable. Every experience starts to feel suspect. Is this table truly real? Or is it just data being rendered into perception? Is the love you feel an authentic emotion, or a simulation produced by a highly advanced algorithm? This is more unsettling than solipsism. Solipsism claims only your mind exists. This idea is worse. It suggests that even your mind might be part of the interface, another pattern within the system. It's the final collapse of support. We didn't just lose our footing, we discovered there was never any ground, and maybe never even any feet. We are ghosts drifting inside another ghost we used to call reality. And the entire world, its beauty, its suffering, its meaning, might be no more real than a dream. Except this is a dream you can't wake up from, because waking up would require another, more real room. What if there are no more rooms? What if this is the only dream that exists? Once you accept the possibility that we live inside an interface, the next step is unavoidable. Every interface implies a user. Every image implies a viewer. If reality is a representation, then who or what is the audience? That question drags the most uncomfortable, most controversial element of all into the center of the picture: the observer. For nearly 400 years, science was built on objectivity, the belief that the universe exists independently and can be studied from the outside, like an impartial spectator watching a stage. The goal was to remove ourselves from the experiment as much as possible, so our measurements wouldn't distort the outcome. The ideal was to describe reality as it is, not as we want it to be. That approach gave us extraordinary power. But we've now reached a point where it stops working, where the very division between observer and observed begins to collapse. Quantum mechanics shows that observation changes what is observed, and the interface hypothesis suggests something even more extreme. Without an observer, there might be nothing at all to observe. This is the edge of the abyss that physics has tried to avoid for almost a century. The most scandalous idea in science: reality may not exist in a definite form until you look. The universe may not be a pre-written fact. It may be a conversation, and we are one side of it. We are stepping into the darkest forest of modern physics, where objectivity dies and something far stranger takes its place. We've arrived at the epicenter of an earthquake that has been shaking science for generations. Everything up to now was preparation. We reduced matter to field excitations. We dissolved space and time into emergent projections. And even then, you could still cling to a modified objective picture. Maybe behind the interface, there's simply another, deeper physical layer. But now we reach something so radical, so offensive to the spirit of the scientific method, that many scientists still try not to look directly at it. We reach the problem of the observer. For almost 4 centuries, modern science rested on a single foundation: objectivity, the dream of a God's eye view. The premise was elegant. There is one universe that exists independently of us. It obeys eternal laws. The scientist is supposed to be a neutral witness, building instruments and theories that remove the observer from the equation. Galileo tracking the planets, Newton extracting universal gravity, Laplace imagining a demon that, knowing every particle's position and velocity, could predict the entire future. This worldview was built on separation: a subject, the scientist, and an object, the universe. Between them was an unbridgeable gap. The scientist could observe, describe, measure, but not alter reality simply by observing it. That principle was science's strength. It separated fact from opinion, knowledge from superstition. It gave us technology, medicine, and a map of the cosmos. It worked until we looked too closely. In the early 20th century, when physicists entered the atomic realm, they found something that didn't fit any framework. Matter at its smallest scale wasn't just strange, it was paradoxical, illogical, and worst of all, it seemed inseparable from the act of observing it. At first, researchers blamed flawed instruments or incomplete theories. But one experiment, repeated endlessly, with incredible precision, kept returning the same verdict. The passive observer is a myth. The most famous, simplest, and most terrifying experiment in physics didn't just reveal a new feature of the universe, it destroyed the old universe. It showed there is no clean gap between you and reality. You cannot merely watch. Your perspective acts like a force. It participates, it creates, and that changes everything. The centerpiece of this collapse is the double slit experiment. Its setup is deceptively simple. Its implications are horrifying. Imagine a barrier with two narrow parallel slits. Behind it sits a detection screen that records where particles land. Start with something familiar: small pellets. Each pellet passes through one slit or the other and hits the screen, producing two clear bands aligned with the slits. Common sense survives. Now send waves instead, like water waves. Waves passing through two slits interfere. Peaks reinforce peaks. Peaks cancel troughs, and the screen displays many alternating bright and dark bands. An interference pattern. Still logical. Now comes the quantum nightmare. Send electrons, fundamental particles of matter, through the slits, and do it one electron at a time so they can't influence each other. Common sense says, electrons are particles. Each electron should go through one slit or the other. After enough electrons, the screen should show two bands. But that's not what happens. Instead, an interference pattern slowly builds up dot by dot, as if each single electron behaved like a wave passing through both slits and interfering with itself. How can a lone electron do that? The only consistent explanation is that the electron does not travel along one definite path. It behaves like a probability wave, exploring multiple possibilities simultaneously until it lands as a single point on the screen. But that's only the beginning. Physicists then tried to outsmart nature. Fine, let's watch which slit the electron goes through. Place a detector at the slits, just to gather information, not to interfere, just to know. And the moment they do it, the interference pattern vanishes completely. Instead, the screen shows two ordinary bands, as if electrons are tiny pellets again. The act of observing, of extracting which path information, changes the electron's behavior. With no detector, electrons behave like waves. With a detector, they behave like particles. Remove observation, wave returns. Add observation, particle returns. Reality behaves differently when it is being watched. That isn't a metaphor. It isn't philosophy. It's an experimental result repeated countless times. Observation is not passive. It is an intervention. It forces the system to choose a definite outcome from a cloud of quantum possibilities. We don't merely observe reality. We compel it into one form. That conclusion is so offensive to intuition that even today we struggle to accept it. It suggests that an objective world existing in a definite state before observation may not exist at all. The double-slit experiment leaves an unbearable message. Observation changes reality. But common sense fought back with a loophole, one Einstein clung to desperately. Maybe the world is objective after all. Maybe particles carry hidden properties we don't see. Maybe the outcome is predetermined. This became the hidden variables idea. The electron is always a particle, always following a definite path. The interference pattern is just the statistical result of many electrons guided by unseen instructions. This view was a lifeline. It preserved realism. It restored a universe that exists on its own. God doesn't play dice. There are simply rules we haven't discovered. For decades, this was a philosophical argument because there was no way to test it. Then, in 1964, John Stuart Bell did something extraordinary. He turned the argument into math. He derived Bell's inequality. Bell's result was brutal. If local realism is true, if particles have hidden variables, realism, and no influence travels faster than light, locality, then the correlations between entangled particles can never exceed a certain limit. That gave physics a clean test. Measure the correlations. If they stay within Bell's bound, Einstein wins. Reality is objective and local. If they violate the bound, Einstein loses, and the universe is either non-local or not real in the classical sense. Since the late 1970s, physicists have run these experiments again and again. Early tests were crude, but they improved over decades. They used photons, electrons, atoms. The separations grew from meters to kilometers. One loophole after another was sealed, and the outcome never changed. Bell's inequality was violated every single time. Not slightly, not ambiguously. The results matched quantum mechanics with eerie precision. Local realism died. It was the final burial of the intuitive universe. Bell's tests force an insane choice. Either abandon realism, accept that particles do not have definite properties until measured, that even the moon doesn't exist in a definite state when no one looks, or abandon locality, accept instantaneous influence across distance. Spooky action that ignores the speed of light. Both options are madness by common sense. But experiment doesn't care about common sense. One of these options is true, and that means the universe is stranger than the human mind was built to tolerate. Bell handed us a nightmare. Either reality is non-local, or it is not fully real until measured. But what if it's worse? What if reality is not even locked in time? The double slit experiment shows that gaining which path information destroys interference. But what if we choose whether to gain that information only after the particle has already traveled its path? That was John Archibald Wheeler's idea. Delayed choice experiments, and their modern relatives, quantum erasers. And they push the absurdity to the edge of insanity. Imagine the two slit setup again, but now with entangled photon pairs. Call them photon A and photon B. Photon A heads toward the slits and detection screen. Photon B takes a longer route to a different part of the lab, arriving later. We can mark photon A at the slits, so we could in principle know which slit it took. When we do that, interference disappears, exactly as expected. But here's the twist. Photon B arrives later, and with photon B we can decide to either preserve the path information or erase it. We can route it to a detector that keeps the which path correlation intact, or to a quantum eraser device that destroys the information so that no one can ever know which slit photon A went through. Now reality breaks. When you look at photon A's hits alone, it appears as a messy scatter of dots. But then you sort the data. Take only the events where photon B went through the eraser, and suddenly an interference pattern emerges from what looked like noise. Take the events where photon B went to the detector. Those show two clean bands, no interference. So photon A hits the screen first. Its past seems decided, and only later do we choose what to do with photon B, erase the information or preserve it. And that future choice determines how photon A behaved back then. Erase the information, and photon A was a wave. Keep the information, and photon A was a particle. This doesn't merely challenge causality, it humiliates it. It implies the past is not fully fixed until it is confirmed by measurement. It remains a haze of quantum possibility until observation locks it into a definite history. Our choices now don't just influence what will happen, they influence what has already happened. The universe isn't a book we read. It's a book that gets written and rewritten as we turn the pages, possibly in both directions. These experiments drive us toward a conclusion that feels like both paranoia and megalomania at once. Reality does not crystallize into a definite form until we interact with it. The present shapes the past. Here affects there. Wheeler summarized decades of these shocks with a concept he called the participating universe. He rejected the idea of the universe as a machine running independently of observers. Instead, he imagined a self-excited circuit. The universe begins with the Big Bang, evolves for billions of years, forms stars, planets, and eventually produces life. That life gives rise to observers. And those observers, by measuring and looking back, by interpreting cosmic signals, help convert the early universe's quantum ambiguity into a definite classical history. The universe creates observers. Observers, in turn, help create the universe's history. A loop, an Ouroboros, a snake biting its own tail. This isn't just poetic. It's an attempt to take experimental data seriously. If choices made now can determine outcomes associated with events long ago, then observation is not merely a passive recording, it is participation. We are not simply watching a film that was finished long before we arrived. We are viewers and editors, and possibly something even closer to co-authors, selecting which of many possible versions becomes the one history calls real. That idea can feel empowering. We are not dust in an indifferent void. We matter to reality itself. But it also brings a crushing responsibility. If our observation participates in reality, what kind of reality are we selecting? Which story are we collapsing out of the endless library of possibilities? And the most disturbing question Wheeler's view raises is this: what existed before the first observer? Did the universe exist in any definite sense during the billions of years before consciousness arose? Or did it become real only when observation finally illuminated it, retroactively, solidifying its past? At this point, physics bleeds into metaphysics, but it is metaphysics forced upon us by the most precise experiments ever performed. And this leads to the next unresolved question. What counts as observation in the first place? What is the mysterious ingredient that turns probability into fact? Where is the line? This is the measurement problem, the skeleton in the closet of quantum mechanics. Follow the chain. An electron is in superposition, both here and there. It interacts with a detector. Now the electron and detector become entangled. The detector is also in superposition. It registered here and registered there. The signal goes to a computer. Now the electron, detector, and computer are one quantum system in superposition. Then you look at the computer screen. Now you and the apparatus are entangled in one gigantic quantum state. You saw here and saw there. Yet subjectively, you never experience superposition. You see one outcome, one reality, one result. So where did the collapse happen? Where did the world choose? John von Neumann studied this chain and concluded that there is no obvious place inside the physical system where collapse must occur. Any measurement device can be described quantum mechanically. That means it too can remain in superposition. A detector, a computer, even your eye and your brain. Complex, yes, but still physical systems made of atoms. And there is no known physical law that says quantum behavior stops at some size or complexity threshold and suddenly becomes classical certainty. Von Neumann suggested that collapse happens only when information reaches something not described by physics, something outside the material chain. He proposed that this something is consciousness. That idea feels shocking, almost forbidden. It seems to smuggle the immaterial into physics. But purely as logic, it is one possible answer. If everything material follows quantum rules, then collapse must involve something beyond material description. This does not prove consciousness creates reality, but it does scream that our current physics is incomplete. We have no final account of why the world becomes definite at all. And the measurement problem becomes even more disturbing once we consider multiple observers. That brings us to the famous thought experiment proposed by Eugene Wigner, Wigner's friend. Picture your friend inside a sealed laboratory, performing a quantum measurement, say, measuring an electron spin. The moment your friend looks at the result, from his perspective, the wave function collapses. Superposition ends. Reality becomes definite. He sees spin up. But from your perspective outside the lab, you have no information about what happened. According to quantum mechanics, until you interact with the lab, you must treat the entire lab as one quantum system. That means the entire lab, including your friend and his brain, is, from your perspective, still in superposition. In one branch, he saw spin up and feels relief. In another branch, he saw spin down and feels crushed. For you, he exists in both realities at once. He knows one outcome, and he knows the opposite. And that's where the nightmare gets worse. From the outside, it's as if your friend is split, like a kind of quantum schizophrenia. And this superposition only resolves when you finally open the door and ask what happened. So what does that mean for you? Does reality choose only at the moment you receive the information? If so, then who is correct? Your friend, for whom the collapse already occurred, or you, for whom collapse happens later? Quantum mechanics, in its standard form, refuses to give a satisfying answer. It tells you that both perspectives are valid inside their own frames of reference. And that pushes you toward a terrifying implication. There may be no single objective reality shared by everyone. Reality becomes relational. A definite fact for one observer remains a mere possibility for another. The world stops being one coherent story and becomes a patchwork of observer-dependent narratives, multiple overlapping realities, each stitched together by the measurements and experiences of those inside it. There is no supreme referee, no all-seeing God's eye view that declares which reality is the real one. Each is real for the observer who lives inside it. That is a universe with no foundations, no universal floor beneath our feet. And this isn't some poetic exaggeration. It follows logically from the core principles of the most successful scientific framework we've ever built. So, we reach a conceptual dead end. On one side, quantum mechanics seems capable of describing everything physically, insisting that systems can exist as superpositions of possibilities. On the other side, conscious experience is always definite. You never experience spin up and spin down simultaneously. You see one result, one outcome, one world. That gap between quantum description and lived experience drives some physicists and philosophers toward a radical, almost forbidden proposal. What if consciousness is not just watching events unfold? What if consciousness is the missing ingredient? The collapsing factor we've been hunting all along. This idea, often linked to the von Neumann-Wigner interpretation, claims that consciousness plays an active and essential role in turning quantum potential into classical fact. In this view, the wave function doesn't collapse when an electron hits a detector, or when a signal enters a computer. The entire physical chain, from subatomic particles to measurement devices to neurons firing in the observer's brain, remains part of a massive entangled superposition. And only when that information enters conscious awareness does something decisive happen. Possibility becomes actuality. Maybe becomes is. Seda, this does not mean you can bend reality with wishful thinking like some fantasy spell. It means something subtler and far more unsettling. The act of conscious perception itself may be the mechanism that forces the universe into a definite state. Without consciousness, reality would remain an endless fog of branching probabilities. A ghost garden where every path exists, but none of them are ever fully realized. In that model, consciousness isn't a minor evolutionary side effect that showed up in primate brains. It becomes fundamental, an irreducible feature of reality, as basic as energy or structure. It becomes a necessary condition for the classical world to appear at all. No surprise, most scientists resist this fiercely, because it feels like a betrayal of materialism. It sounds unscientific, but it's crucial to understand what it actually is. Not religion, not mysticism, just one logically consistent attempt to solve the measurement problem. It might be wrong, but the fact that serious thinkers even consider it shows how deeply quantum mechanics forces us to re-examine the foundations of reality, including what we are. And if this hypothesis were true, the implication is staggering. We wouldn't merely participate in reality. We would be the spark that ignites it. We would be how a universe that is just math becomes lived experience. Now collect the wreckage and look at the pattern. Classical science promised an objective universe that exists independently of us. Quantum mechanics shattered that promise. The double slit experiment revealed that observation changes outcomes. Bell's theorem showed that particles don't carry pre-assigned properties. Reality is not settled until measurement. Quantum eraser and delayed choice experiments suggest that present choices can determine how the past must be described. Wheeler's participatory universe reframed observers as essential in constructing cosmic history. The measurement problem exposed a brutal gap. Our physical laws don't explain why the world ever becomes definite. And Wigner's friend pushes the logic to the edge by implying reality may be observer relative. Put together, these threads lead to a conclusion that flips the scientific worldview upside down. There is no fully observer-independent reality. The universe is not, at bottom, a collection of hard facts. It is a domain of pure potential, an ocean of possibilities, and observation acts like a catalyst that makes that potential crystallize into concrete events. We don't merely investigate the world, we interact with it at the deepest level. And that interaction is what produces what we call reality. That destroys the idea of purely passive knowledge. We are not drawing a map of an already existing territory. The act of making the map changes the territory itself. Suddenly, the scientist can't hide behind the mask of neutral witness. We stand at the center of the process, not as rulers of creation, but as indispensable participants. Every glance, every measurement, every choice, every act of attention becomes a brush stroke on the canvas of what becomes real. And when you look around now, you're standing on a mountain of broken assumptions. No solid matter, no absolute space-time, no universal objective reality. So what's left? Only the process remains. Interaction, the dialogue between potential and fact, between system and observer. Reality is not what is, it is what becomes known. We stop searching for the ultimate stuff of the universe and start investigating the rules of interaction that generate what appears. This conclusion produces two feelings at once: loneliness and a kind of frightening power. Loneliness because there is no longer an external bedrock of objective truth to cling to. We drift in a sea of relational realities. But power because we are no longer merely passive victims of a universe that happens to us. We are central players in the event of reality itself. Our perception converts the quantum maybe into the classical is. It's freedom that feels like a threat, because you can no longer treat the world as something you simply accept. You have to acknowledge your role in how it keeps coming into being. And that brings us to the next and strangest stage. If reality is fundamentally an interactive process, if the universe behaves like a system that responds to measurement by producing outcomes, and if that system is held together by a web of non-local informational connections, then doesn't this start to resemble computation? Doesn't it feel like the universe is doing something like processing? Like physical laws are algorithms? Like reality is what a calculation looks like from the inside? We've reached the final layer of the descent, an idea that used to sound like science fiction, but is now discussed seriously by physicists and cosmologists. What if the universe is unreal because it is, in some sense, a simulation? Pop culture usually frames this as a fake world running on someone else's computer, in some higher, real universe. But the version physics pushes toward is stranger. It's not that our universe is simulated inside another universe. The claim is that our universe is, at its core, a computational system. Computation isn't something happening within it. Computation is what it is. Call this the computational universe hypothesis. It ties together the oddities we've uncovered into one eerily coherent picture. Why does reality look informational rather than material? Because computation is built from bits, not atoms. Why are space and time emergent instead of fundamental? Because computing systems generate their own internal structures, something like space-time, out of simpler rules. Think about video games. They have space, time, physics, movement, causality. But beneath it all, it's just code executing. Why does reality seem non-local, with correlations that ignore distance? Because in computation, informational relationships aren't constrained by geometry. Variables can be linked regardless of where they are. Why is reality not definite until measurement? Because a system can conserve resources by not determining an outcome until it's requested. In programming, this is called lazy evaluation. The system doesn't render what isn't being queried. In this view, the weirdness of quantum mechanics isn't an accident. It's not a flaw. It's an expected signature of computation, observed from within the patterns it generates. So we're ready to take the hypothesis seriously, that reality is not fundamentally physical, but computational. That everything, including us, is a complex informational pattern unfolding according to rules. Well, that the universe is executable code. We are entering the fourth and most abstract act of the investigation. The possibility that the universe isn't merely described by mathematics and information, but is mathematics and information. Not a physical world with equations, but a self-contained calculation. It sounds outrageous. So treat it like a detective case. If you were a program living inside a computer, How would you figure out your world isn't base reality? You would search for artifacts, clues that betray a computational substrate. And the first clue is powerful. At the deepest level, reality looks digital, not analog. An analog system is continuous. You can zoom in forever and still see smooth transitions. A digital system is discrete. It's made of indivisible units. Zoom in far enough and you see the grain, the pixels. For centuries, we assumed reality was continuous. Quantum mechanics says otherwise. Energy doesn't flow in smooth gradients. It comes in discrete packets, quanta. Electric charge isn't continuous. It comes in fixed units based on the electron's charge. Even particles behave like quantized excitations. And most strikingly, space-time itself appears, at the Planck scale, to be discrete, quanta of space and quanta of time. That means reality has a finite resolution. There is a smallest pixel. It's not obvious at human scale, but it is a natural consequence of our best theories, and it screams digital architecture. The world is not infinitely divisible matter floating through perfectly smooth space. It is a finite set of discrete states transitioning in discrete steps. Exactly how a computational system works. Computers operate on bits flipping between states. If reality is computational, this is precisely the kind of structure you would expect to find at its core. And, disturbingly, we do find it. This doesn't prove we live in a simulation, but it is a strong and unsettling hint. The smooth, analog-feeling world may be high-quality rendering, an illusion produced by a fundamentally digital machine. The second clue is even stranger, because it involves information itself. In everyday life, we treat information like something abstract. In physics, information is physical. A bit must be instantiated in a physical system, an electron's spin, a molecule's configuration, a field state. Information must obey physical laws, and black holes led to one of the most shocking discoveries. There appears to be a hard limit to information. You cannot pack infinite information into a finite region. Jacob Bekenstein calculated an absolute upper bound, now called the Bekenstein bound, on how much information can be stored in a region of space with a given energy. Like a hard drive, the universe seems to have storage limits. And the most bizarre part is what that limit depends on. Not the volume, but the surface area enclosing it. That's the same logic behind the holographic principle. But even before the hologram, the crucial point is this: a limit exists at all. If the universe were an infinitely precise analog system, there should be no upper bound. You could always store more information by recording reality at ever finer resolution. But in a digital computational system, a cap is exactly what you'd expect. Finite resolution implies finite capacity. And that is why the existence of a strict information limit does not feel like a minor technical constraint. It feels like a signature, a fingerprint left behind by the nature of reality itself. Every computer operates with finite memory and finite processing power. The existence of the Bekenstein limit strongly suggests that our universe may also function under limited resources, as if it possesses a maximum amount of memory and a maximum processing speed defined by Planck time. This explains why reality becomes grainy and discrete at the Planck scale. The system simply cannot resolve information beyond that resolution. There are not enough resources to do so. This perspective also reframes the very nature of physical laws. Why do such laws exist at all? Within a computational universe, the laws of physics are not mystical commandments imposed from outside reality. They function as algorithms for compressing information. They represent the most efficient way to describe how the system evolves. Just as we compress files by identifying patterns and replacing vast amounts of data with short rules, the universe may operate by identifying regularities and encoding them into compact mathematical laws. In this sense, physics may be nothing more than a highly optimized compression scheme for reality itself. This interpretation strips away much of the mystery, but it also makes the universe far more mechanical. We are not living in an infinite, boundless cosmos. We exist inside a system with finite resources, governed by optimization rules and efficiency constraints. Not a divine stage, but an extraordinarily effective machine. The third line of evidence supporting a computational interpretation of reality lies in the structure of physical laws themselves. We usually treat these laws as passive descriptions of how the universe behaves. But what if they are not descriptions at all? What if they are instructions? Every fundamental equation in physics, from Newton's laws to Schrödinger's equation, can be understood as a rule that takes the current state of a system and computes its next state. This is precisely how an algorithm functions. It accepts input, applies a rule, and produces output. The universe begins to resemble a massive system executing its own code step by step. This idea becomes especially clear when we consider cellular automata, a concept popularized by mathematician John Conway through his Game of Life. A cellular automaton is an extremely simple computational system. It consists of a grid of cells, each of which can exist in a small number of states, such as on or off. A small set of local rules determines how each cell changes based solely on the states of its neighbors. In Conway's Game of Life, for example, a dead cell with exactly 3 living neighbors becomes alive. A living cell with fewer than 2 or more than 3 living neighbors dies. That is the entire rule set. There is no central controller, no goal, no guiding intelligence, only local interactions. Yet from these minimal rules, astonishing complexity emerges. Patterns appear that move across the grid, replicate themselves, construct other patterns, and even perform computations. Simple deterministic rules generate behavior that appears purposeful, adaptive, and alive. Now imagine extending this idea beyond a 2-dimensional grid. Imagine a cellular automaton defined on a complex network or hypergraph with slightly richer update rules. Could a system like that generate something indistinguishable from our universe? Could particles, fields, and even space-time itself emerge as large-scale patterns in such a computational substrate? This is not merely speculative philosophy. Physicists such as Stephen Wolfram have been actively developing models along these lines in projects aimed at uncovering the fundamental computational structure of reality. These models demonstrate how simple abstract networks, evolving according to minimal rules, can reproduce the mathematical structures of quantum mechanics, special relativity, and even general relativity. This reverses our intuition about complexity. We tend to believe that complex phenomena must arise from complex causes. Computational thinking suggests the opposite. An immensely complex universe can emerge from an astonishingly simple algorithm, provided it runs long enough. If this is true, then our reality may be nothing more than the output of an ancient and elegant computation, unfolding step by step according to rules that existed long before stars, planets, or observers. This leads us to an even deeper question. If the universe is a computational system, what is its most basic unit? What is the equivalent of a bit, the on or off cell at the foundation of everything? Here we arrive at one of the most profound ideas ever proposed in physics, captured in John Archibald Wheeler's famous phrase, "it from bit." According to this idea, every physical entity, an electron, a photon, a galaxy, ultimately arises from bits of information, binary distinctions, yes or no, 1 or 0. In this view, neither matter nor energy is fundamental. Information is. Everything is ultimately constructed from answers to binary questions we ask nature. Did the electron go through the left slit? Yes or no? Is the spin up or down? Yes or no? These answers are not descriptions of an underlying object. They are the object. An electron is not a tiny particle hiding somewhere in space. It is a structured set of informational outcomes. Reality is not made of things. It is made of answers. This aligns perfectly with quantum mechanics, where particles do not possess definite properties until measured. Measurement is the act of asking a question and receiving a response. Information is created at that moment, and only then does reality become defined. From this perspective, the universe is not a mechanical clockwork. It is a vast information processing system. Every interaction is not merely a collision, but a computation. The laws of physics are not rules governing matter. They are protocols governing the flow and transformation of information. This framework is known as digital physics. It proposes that there is no ultimate substance beneath reality, no final layer of matter. At the bottom of the rabbit hole, there is only information, bits, decisions, logical distinctions. And somehow, from this simple binary foundation, the entire richness of our universe emerges. When viewed through this lens, the strangest features of quantum mechanics stop looking like paradoxes. They begin to look inevitable. Why is reality undefined until observed? Because the system delays computation until a query is made. Why can particles exist in superposition? Because unresolved states are stored efficiently, like compressed data. Why does entanglement violate spatial intuition? Because information connections are not constrained by emergent geometry. Why can the past appear to depend on future measurements? Because the system updates its internal database to maintain global consistency. These are not flaws. They are features. We thought the universe was a machine made of matter. It appears to be a computation made of information. Quantum weirdness is not a breakdown of reality. It is what computation looks like from the inside. This idea reaches its most ambitious form in Stephen Wolfram's computational models of physics. In these models, reality begins with nothing but abstract relationships between abstract points, forming a vast evolving network. A single simple rule updates this network step by step. From this alone, without space, time, particles, or fields, structures emerge that behave exactly like our physical universe. Space appears as the network grows. Time emerges as the sequence of updates. Particles arise as persistent patterns moving through the network. Gravity emerges as a statistical property of the network's evolution. Nothing is fundamental except the computation itself. This is not just philosophy. It is an attempt to explain all known physics from a single, minimal computational principle. And if this framework is correct, then space, time, matter, and energy are not the foundations of reality. They are secondary effects. They are what computation looks like once it becomes sufficiently complex to reflect upon itself. This model is not just abstract speculation. It makes concrete predictions that can, at least in principle, be tested. It suggests that at the deepest level of nature, there may be subtle deviations from the predictions of special relativity. It allows for the existence of particles with masses that do not fit within the standard model. And if even a single one of these predictions were experimentally confirmed, it would trigger a genuine revolution in physics. It would mean that we had finally glimpsed what lies behind the interface, a fragment of the underlying code of reality itself. We have now climbed to the highest level of abstraction, to a point where ordinary language begins to fail. We followed a path from solid objects to vibrating fields, from fields to emergent spacetime woven out of quantum connections, and from those connections to calculations governed by simple rules. At this stage, we must ask the final question of this entire construction. What carries the calculation itself? What is the ultimate bit at the bottom of everything? The answer was proposed decades ago by John Archibald Wheeler in his idea of it from bit. To grasp its full meaning, we must reverse our usual way of thinking. We tend to assume that reality exists first, and only afterward do we ask questions about it. Wheeler suggested the opposite. First come the questions, binary questions with yes or no answers, and reality emerges from the accumulation of those answers. Imagine the universe as an enormous game of 20 questions. But unlike the ordinary game, there is no predefined object waiting to be guessed. The object itself comes into existence through the act of questioning. Every interaction in the universe, whether it is a collision between particles or a measurement in a laboratory, is the universe asking itself a question and producing an answer. Each answer represents one bit of information, and the totality of these bits is what we call the universe. In this picture, there is no underlying substance. There is no matter in the traditional sense. There is only information. Reality is not something we uncover. It is something that is constructed through interaction. Each measurement is not a passive reading of a pre-existing fact. It is an act of creation that adds a new bit to the structure of the world. This explains why reality is undefined until observation. Before the question is asked, there is no answer to exist. The universe is not a book whose story has already been written. It is a blank page on which history is continuously written through interactions. This marks the complete dismantling of the material worldview. There is no solid foundation beneath the surface. There is no final particle hiding at the bottom. There is only an intangible process of information exchange. Reality is not a noun. It is a verb. It is an ongoing process, and we are not spectators standing outside of it. We are part of the process itself. We do not merely exist within the universe. We are the entities whose questions force it to take form. And that is perhaps the most unsettling implication of all. If reality is fundamentally informational, then the physical world is nothing more than an immense information structure, extraordinarily rich and intricate, yet no more concrete than a program or a mathematical proof. Once we adopt the hypothesis of a computational universe, the paradoxes that once haunted us begin to align into a single coherent picture. What once appeared chaotic now appears ordered. The madness of the quantum world dissolves into logic. Consider the illusion of matter. Why does the world appear empty, composed of fields rather than solid substance? Because objects are not fundamental. Information and the rules governing its transformation are. Matter is simply a stable pattern within this informational flow. Like an icon on a computer desktop. It appears to be an object, but in truth, it merely points to data. Consider the illusion of space-time. Why are space and time not fundamental? Why does non-locality exist? Because space-time is a data structure the system uses to organize calculations at large scales. It is useful for constructing a macroscopic world, but it does not exist at the level of the underlying code. At that level, information connects directly, not geometrically. Consider the illusion of objectivity. Why does reality depend on observation? Because the system optimizes its resources. It does not compute every possible outcome in advance. It performs calculations on demand. Observation is the request that forces the system to render a specific result. Within this framework, the paradoxes vanish. There is only a single system operating consistently, and we observe it from within. It is like a character inside a video game, attempting to understand their world. They would encounter invisible walls, sudden appearances, strange physical glitches. To them, these would be paradoxes. To the player, they are simply features of the game engine. The computational universe hypothesis allows us to view our own world in the same way. Quantum strangeness is not evidence of irrationality, it is evidence of efficiency. These are not errors in the universe, they are features of its operating system. This idea finds its most ambitious expression in the work of Stephen Wolfram. For decades, he has argued that we have been searching for fundamental reality in the wrong place. Instead of increasingly complex equations, we should ask whether the universe can emerge from extremely simple rules executed repeatedly. In Wolfram's framework, reality begins with abstract relationships between abstract points, forming a vast evolving network. A single simple rule updates this network step by step. From this alone, without predefined space, time, particles, or forces, structures emerge that behave exactly like our physical universe. The network itself begins to function as space. The number and arrangement of connections determine effective dimensionality. Patterns propagating through the network behave like particles. Their interactions reproduce the rules of quantum mechanics. Even gravity arises naturally as a statistical property of how the network grows and bends. In this picture, nothing familiar is fundamental. Space, time, matter, and energy are emergent macroscopic features of a deeper computational process. This is not merely philosophical speculation. It is an attempt to derive all known physics from a single minimal principle. If this view is correct, then the universe is not a place that contains computers. The universe is the computer. What we call physical reality is simply the output of its computation, its graphical interface. We began with the illusion of matter and discovered that information lies beneath it. That is the file. We moved on to the illusion of spacetime and realized it is an emergent data structure. That is the file system. We then confronted the illusion of objectivity and learned that reality does not exist prior to observation. That is on-demand rendering. Finally, we assembled these insights into a single hypothesis, the computational universe. That is the operating system. This hypothesis is remarkably economical. It introduces no new laws and no exotic entities. Instead, it explains existing laws as emergent features of a simpler underlying process. It explains why mathematics is so effective in describing reality, because reality itself is mathematical. It explains time as a sequence of computational steps and space as a network of informational relationships. It even offers a potential framework for understanding consciousness as a self-referential computational pattern. Of course, this remains a hypothesis. It is not proven. but its explanatory power is immense. It transforms a collection of disconnected mysteries into a single, coherent, if deeply counterintuitive system. It urges us to stop asking what reality is made of and start asking how it is computed. We are moving beyond physics into something closer to information physics. And this shift may be as profound as the revolutions initiated by Copernicus and Newton. We have now reached the climax of this investigation. If the universe is an illusion, it may be because it is fundamentally an interface to an underlying computational process. This realization brings a strange sense of intellectual clarity and also a new wave of unsettling questions. If reality is a calculation, is it deterministic, or does it allow true randomness? If everything follows an algorithm, what becomes of free will? Is it merely an emergent sensation produced by complexity? Or does unpredictability itself arise naturally from computation? What is the purpose of this calculation, if any? Was the universe initiated to solve a problem, to generate consciousness, or does it simply exist as a self-running process with no goal at all? And finally, the question that seems impossible to avoid. If the universe is a program, who or what wrote the code? This question pushes us beyond science into metaphysics. The computational hypothesis does not answer it, but it reframes it. Perhaps we search for a programmer, only because every program we know has a creator. But what if the universe is a different kind of computation, one that does not require an external author? This brings us to the final and most unsettling possibility of all. What if there is no architect behind reality? What if logic and mathematics alone are sufficient to generate existence? What if mathematics is not merely a language describing the universe, but the universe itself? This leads directly to the final idea we must confront: Max Tegmark's mathematical universe hypothesis, the claim that any mathematically consistent structure exists physically. We now have to face what that implies for our own existence. Are we simply self-aware substructures inside a vast mathematical object? And then comes the most fundamental question of all. Why does anything exist at all instead of nothing? And we must consider a possibility that feels almost offensive to intuition, that this unbelievably complex computational structure could have emerged from absolute, total nothingness. This is the final stage of dismantling. After this, there may be nothing left except raw astonishment, and maybe raw horror. Because we've arrived at what seems like the final logical question. If the universe is a calculation, then where is the supercomputer running it? That question haunts almost everyone the first time they encounter this idea. It summons images of giant servers hidden in some higher realm. It conjures creator programmers watching our lives on cosmic monitors. But despite how natural it sounds, it's a trap, a leftover reflex from the macroscopic world, forced onto a level of reality where it no longer applies. We are trained into dualism. There is the program, and there is the machine that runs it. There is software, and there is hardware. There is code, and there are silicon chips. One is abstract, the other is physical. But what if that division is not fundamental? What if the universe is a special kind of computation that does not require an external medium? What if it is both software and hardware at once? Think about a mathematical structure like the Mandelbrot set. It is an infinitely complex fractal, defined by an extremely simple equation. Where does it exist? It is not located anywhere in physical space. It exists in the abstract realm of mathematical truth. It does not need a computer in order to exist. We use computers only to render it, to visualize it, to translate it into something our senses can perceive. But the structure itself, with all its endless detail, exists timelessly, whether anyone looks at it or not. Now imagine our universe is the same kind of thing, far more complex, but essentially the same category of entity. It is not running on anything. It simply is. Its existence is its computation. Every interaction, every particle collision, every moment is not something being simulated on a separate machine. It is the unfolding of the structure's own internal logic. In this view, there is no separation between the description and the described. The equations of physics are not a model of the universe. They are the universe. Reality is not being computed by something else. Reality is the computation. This is how you escape infinite regress. Because once you ask, who simulates our universe, you immediately trigger the next question. Then who simulates the simulator's universe? And then another, and another, forever. The hypothesis of a self-sufficient universe cuts that loop cleanly. There are no nested simulation levels. There is only one fundamental reality, the reality of mathematical and logical consistency. And we are not outside it. We are inside it. We are part of it. That kicks the last support out from under our feet. We were looking for a creator, a programmer, a machine hidden backstage, and we find nothing like that. Only a pure, cold, impersonal, eternal structure. No curtain to pull back. No behind the scenes. The stage is all that exists. This idea, the universe as a self-contained mathematical structure, found its boldest, most formal expression in the mathematical universe hypothesis proposed by cosmologist Max Tegmark. This is the final and most radical step away from intuitive realism. It says this: any mathematical structure that is logically self-consistent does not merely describe a possible universe. It is a universe. Mathematical existence and physical existence are the same thing. Tegmark calls this a kind of mathematical democracy. Any consistent mathematics has equal right to physical existence. And the practical meaning of that is brutal. Our universe is not special, not chosen, not privileged. It is one structure among an infinite collection of structures, all equally real in the Platonic library of everything that can exist logically. Alongside our universe, there would be worlds governed purely by Newtonian mechanics. Worlds that are nothing but cellular automata. Worlds with radically different dimensionalities and rule sets, some simpler, some incomprehensibly complex. Anything that can be described consistently in mathematical language exists as a physical reality in its own right. We do not live in a universe that can be described by mathematics. We live in a universe that is mathematics. That thought is intellectually freezing. It introduces a kind of cosmic loneliness. It strips our universe of the comforting idea of purpose, selection, intention. It wasn't made. It wasn't chosen. It is simply one of infinite logical possibilities, except for one detail. This particular mathematics turned out to be rich enough to generate substructures capable of recognizing their own existence. That is us. In Tegmark's framework, we are self-aware substructures inside a gigantic mathematical object. Our existence is not a miracle added onto the system. It is a property of the structure itself. The hypothesis is elegant because it seems to require no arbitrary starting assumptions. It explains why mathematics describes reality so well. Because reality is mathematics. It explains apparent fine-tuning. In an infinite ensemble of structures, we can only find ourselves inside ones that allow self-aware substructures to emerge. But the price of this elegance is steep. We lose uniqueness. We become an inevitable consequence of all possible logics existing. We become something like a theorem that proves itself. And if we accept that, we are forced to face the most disturbing consequence. The one that strikes directly at identity. If the universe is mathematics, then what am I? What is my consciousness, my memories, my emotions, my sense of free will? The answer, within this hypothesis, is simple, ruthless, and clean. They are mathematical patterns too. We are self-aware substructures, SS, inside a vast mathematical object. A structure is just relationships between elements. A musical score is a structure. A language is a structure. A social network is a structure. Your brain, with its billions of neurons and trillions of synaptic relationships, is an unimaginably complex structure. And self-aware means that the structure is complex enough to compute information about itself. It forms an internal model of itself and its environment. It can represent, remember, predict, and adapt. From this angle, consciousness is not mystical substance. It is an emergent property of certain recursive information processes. It is what a sufficiently complex mathematical structure does when it contains models of itself. And that creates the identity shock. Love becomes a powerful correlation pattern between two informational systems. Pain becomes a specific computational signal that indicates damage to the system. Free will becomes the feeling produced by a process too complex to fully predict itself from the inside. We are not souls housed in matter. We may be algorithms expressed through mathematics. But does that make us unreal? No. Within this framework, we are as real as anything can be, because mathematical structures are what reality is made of. Our experiences are real as experiences. Our thoughts are real as patterns. Our suffering is real as process. It is not a trick. It is not fake. It is simply not the kind of thing we assumed it was. Think of a character in a novel. The character is not physical, but the story is real as an informational structure. The tragedy is real in the only sense tragedies can be real, inside the narrative that contains them. And if the narrative were complex enough, you could imagine a character awakening to the fact that they are a story and asking, "Who am I?" And the correct answer would be, "You are this pattern." That answer does not reduce reality, it defines it. Still, the fear comes naturally. If the foundation is not real in the usual sense, then our values must collapse too. If everything is just equations, what difference does it make how we live? What is the difference between love and hate, compassion and cruelty? But that fear is built on a misunderstanding. The unreality of the foundation does not erase the reality of emergent levels. A Beethoven symphony can be reduced to air pressure variations and equations. That reduction does not delete the beauty. Beauty is an emergent property that exists at a higher level of organization, inside perception. War and peace can be reduced to ink on paper and symbolic marks. That reduction does not delete the characters, the meaning, the emotional impact. Meaning exists at the level of information and interpretation. Likewise, even if the universe is ultimately a mathematical structure, that does not negate the reality of lived experience. Pain is real as an informational event. Love is real as a relational pattern. Meaning is real as an emergent property produced by self-aware computation. Levels of reality do not cancel each other. They stack. Knowing the chemistry of water does not make thirst less real. Knowing the physics of rainbows does not make them less beautiful. And knowing we might be mathematical patterns does not make our lives meaningless. If anything, it can deepen meaning, because it suggests something wild. Consciousness is not a meaningless byproduct of blind matter. Consciousness is one of the most intricate patterns this structure can generate. We are the way the universe becomes aware of itself locally. We are the universe folding back on itself, producing eyes, memory, curiosity, and awe. But that brings us to the final existential problem: meaning. If reality is an impersonal mathematical object with no creator and no intention, then where does meaning come from? Humanity has always tried to outsource meaning. To gods, to destiny, to nature, to history. We wanted meaning to be objective, external, pre-written. This hypothesis offers no such comfort. The structure simply exists. It is not moral. It has no goals. It does not care. That sounds like despair. But it can also be liberation. Because if there is no objective meaning, then there is no correct meaning we failed to discover. Meaning is not something you find hidden in the universe like a secret message. Meaning is something self-aware structures generate. It is what minds do. It is what consciousness produces when it encounters indifferent mathematics and turns it into beauty, purpose, value, love, art, and knowledge. In this view, meaning is not a fundamental property of the universe. Meaning is our function. We are machines that generate meaning. And that means responsibility falls back onto us. No cosmic authority can guarantee purpose. No external script will rescue us. We cannot offload the job. That is the terror and the grandeur of freedom. We are thrown into an indifferent structure, yet free to carve meaning into it. And now we reach the last question, the one that refuses to die. Why does anything exist at all, rather than nothing? Why does this mathematical structure exist instead of absolute emptiness? The traditional answer is a creator or a necessary eternal cause. But the computational and mathematical view invites a different and almost scandalous approach. What if the whole structure arose from nothing? Not from the quantum vacuum, which is already something full of fields and potential, but from true philosophical nothingness. No space, no time, no matter, no energy, no laws, no logic, not even the concept of existence. It sounds impossible. Nothing comes from nothing. But consider what nothing actually means. Perfect symmetry. No distinctions. No features. no privileged state. In a sense, nothing is the most rigid, featureless condition imaginable, and something is a break in that symmetry. The emergence of a universe would then be a spontaneous symmetry breaking, an instability in the perfect uniformity of non-existence. Some physicists have proposed that the total energy of the universe may be exactly zero. Positive energy and matter, and radiation balanced by negative gravitational energy. If the net sum is zero, then in a sense the universe costs nothing. No energy debt is required. It can appear without violating conservation laws. But even that still assumes the existence of laws. So push one step further. What if the only thing that can arise without cause is logical consistency itself? Because nothingness cannot contain contradictions. A contradictory universe cannot exist even as a coherent concept. That means the only something that can be compatible with nothing, without smuggling in extra assumptions, would be a logically self-consistent structure: mathematics. In this view, the universe did not merely emerge from nothing. It emerged because consistent structures are the only things that can exist without external justification. And that is the final twist. Reality may be a logically consistent structure that requires no creator, exists nowhere and never in the ordinary sense, and arises not from presence, but from absence. Existence itself may be the ripple, temporary, intricate, astonishing, on the surface of nothing. And now we look back at the path we traveled. We began with the solid, reliable world of common sense. Then physics broke it down. Matter became fields. Space and time became emergent. Objectivity became questionable. Observation became participation. Reality became information. Information became computation. Computation became mathematics. And mathematics leads us to the possibility of everything arising from nothing. So, what do we do with this? The first reaction is rejection. Existential vertigo, a feeling that the floor is gone. But the second reaction can be acceptance, not comfort, not reassurance, acceptance. Because science has always done this. It destroys the childlike picture first, and then reveals a deeper landscape behind it. At one time, it was terrifying to learn Earth is not the center. Later, it became majestic. The same may be happening here. Reality may be stranger, colder, more abstract than we ever wanted, but our experience still matters. Our love still matters. Our choices still matter, because they are real patterns inside the only reality we have. And maybe the most profound deception was never simulation or programming. Maybe the greatest deception was the belief that we are separate from the universe at all. At the quantum level, there is no hard boundary. At the informational level, we are substructures. At the mathematical level, we are the structure waking up locally. When you stare into the night sky, it isn't just photons hitting your eye. It is the universe looking at itself through one of its own patterns. When a scientist discovers an equation, it isn't just a human describing the world. It is the world revealing its own logic through a mind it generated. And that realization flips the horror into something else. Not comfort, but awe. We began with the fear that the universe might be an illusion. And yes, along the way, everything collapsed. Matter, space, time, objectivity, separateness. It is terrifying, but it is also beautiful. Because if something this vast, this intricate, this conscious can emerge, perhaps from nothing, then that is not just horror. That is the deepest kind of wonder. And living inside this mystery, participating in it, trying to understand it, building meaning inside it, may be the highest privilege a self-aware substructure can have.